Imagine for a moment that you could freeze the entire universe. Not just slow it down, not just pause a single moment, but truly bring all of existence to a complete and absolute standstill. Every electron in mid-orbit halted. Every photon of sunlight is suspended in its arc across the vacuum. Every atom in your own body is locked rigidly in place, your last thought hanging unfinished in the synapses of your brain. The roaring furnaces of distant stars would fall silent. Galaxies spiraling across hundreds of millions of light years would cease mid-rotation. Even the quantum foam itself, that churning sea of virtual particles at the smallest scales of reality, would go still. And now ask yourself a question that has troubled the greatest minds in the history of human thought. In that frozen cosmos, in that universe where absolutely nothing changes, where nothing moves, where nothing happens at all, does time still exist? Is there still a clock ticking somewhere in the void, counting off seconds that nobody experiences? Or has time itself vanished along with all motion, leaving only a silent three-dimensional tableau of space filled with motionless matter, preserved forever in a single eternal instant that never ends because there is no such thing as ending? The answer to this question may be the most unsettling discovery in modern physics. Because, according to our most advanced theories of gravity and quantum mechanics, the universe at its most fundamental level may be exactly like that frozen scene. Time, as we experience it, as we feel it flowing past us every waking moment, may not be a fundamental feature of reality at all. It may be an illusion, a trick of perspective, something that emerges only for observers embedded inside the universe, while the cosmos itself, viewed from some impossible outside vantage point, sits utterly still in a timeless state of being. This is not the fringe speculation of crackpots or philosophers wrestling with abstract word games. This is the conclusion that some of the most brilliant physicists alive today, including Nobel laureates and founders of entire fields of research, have been forced to grapple with when they follow the mathematics of quantum gravity to their natural conclusions. The equations that describe how gravity and quantum mechanics might finally be unified. Equations like the famous Wheeler-DeWitt equation contain no variable for time at all. The mathematics simply refuses to include it, as if time were an unwelcome guest that the deeper laws of nature had politely shown to the door. Think about how strange this really is. For the past 4 centuries, ever since Galileo rolled balls down inclined planes and Newton watched apples fall from trees, physics has relied on time as one of its most basic building blocks. Every equation of motion you have ever seen, every predicted trajectory, every calculated orbit, has time right there in the mathematics as a fundamental parameter. The position of an object is always some function of time. The velocity is the rate of change of position with time. The acceleration is the rate of change of velocity with time. Remove time from the equations of classical physics, and the entire edifice collapses into meaningless marks on paper. Time is so deeply embedded in our scientific worldview that it seems almost impossible to imagine doing physics without it. And yet here we are, in the 21st century, with some of the most sophisticated mathematical frameworks ever devised by human minds, suggesting that time must eventually be eliminated from our fundamental theories of nature. The attempts to combine Einstein's general theory of relativity with the quantum mechanics that governs the subatomic world keep running into the same strange result. When you push the mathematics to its limits, when you try to describe the deepest, smallest, most fundamental scales of reality, time simply refuses to cooperate. It becomes meaningless. It dissolves into something else. And physicists have spent decades trying to figure out whether this means time is not really there at all, or whether our theories are missing something crucial that would bring time back into the picture. And so we arrive at the question that frames everything we are about to explore together. Can space and matter exist without time? Can there be a universe, a reality, a something rather than nothing, in the absence of this strange flowing dimension we take so entirely for granted? The question sounds almost childishly simple when you first hear it. Of course, there needs to be time, you might think. How could anything exist without a moment in which to exist? How could matter occupy space if there were no duration during which it occupied anything? And yet, when you begin to pull on this thread, the entire tapestry of our common sense begins to unravel in the most remarkable ways. You see, for most of human history, people assumed that time was an obvious, self-evident, unchangeable backdrop to everything else. Days followed nights. Seasons passed in their ancient cycles. People were born, grew old, and died. The sun rose and set with mechanical regularity. What could be more fundamental than the steady, uniform, unrelenting forward march of time? The ancient Egyptians built their entire civilization around tracking it with sundials and water clocks. The Greeks refined these instruments. The Romans organized armies and empires around precise schedules. Time was simply there, a river that carried everything downstream, whether we liked it or not. But modern physics has demolished that comfortable certainty. We now know that time is not a single universal current flowing uniformly through the cosmos. We know that clocks run at different speeds, depending on how fast you are moving and how close you sit to a massive object. We know that two observers watching the same events can genuinely disagree about which event came first. We know that the mathematical equations that describe the most fundamental laws of nature do not seem to care whether time runs forward or backward. And most disturbingly of all, we have begun to suspect that time may not be a fundamental ingredient of the universe at all, but rather something that emerges out of deeper, timeless relationships. The way that temperature emerges out of the motion of countless individual molecules, even though no single molecule has a temperature of its own. So strap in, because what you are about to embark upon is one of the strangest, most challenging, and most mind-altering journeys in all of science and philosophy. We are going to trace this question from the ancient Greek philosophers, who first dared to ask whether change was real or illusion, through the titanic intellectual battle between Isaac Newton and Gottfried Leibniz, over whether space and time could exist independently of matter, to Albert Einstein's revolutionary discovery that space and time are woven together as a single, four-dimensional fabric, and finally into the cutting edge of 21st century physics, where researchers at institutions from Cambridge to Naples are conducting experiments suggesting that time itself emerges from quantum entanglement between the parts of the universe. Along the way, we will meet physicists who have dedicated their entire careers to the radical proposition that time simply does not exist. We will explore experiments with entangled photons that appear to show time being born out of quantum correlations. We will examine the bizarre possibility of a block universe in which the past, present, and future are all equally real and all equally present at once, with our sense of flowing time being nothing more than a peculiar hallucination produced by conscious brains. And we will confront the deeply unsettling implication that if time is not fundamental, then neither is change, neither is cause and effect, nor is the very process of becoming that seems to define every aspect of our lived experience. This is a question that forces us to reconsider what it means for anything to exist at all. It reaches into the deepest layers of reality and asks whether the foundations we have always assumed are actually there. And whatever answer turns out to be correct, whether time is fundamental or emergent, or perhaps something stranger than either, the investigation itself will change how you see everything. The ticking clock on your wall, the wrinkles on the hands of someone you love, the memory of yesterday, and the anticipation of tomorrow. All of it rests upon assumptions that physics has now called into serious doubt. The journey begins, fittingly enough, long before there was anything resembling modern science at all. It begins in the sun-drenched Mediterranean world of ancient Greece, where two thinkers stared at the ever-flowing waters of rivers and the eternal permanence of mountains, and drew diametrically opposite conclusions about the true nature of reality. One said that everything flows. The other said that nothing truly changes. Between them, they set the stage for every single question that physics would ask about time for the next 2,500 years. Around the 5th century before the Common Era, in the coastal city of Ephesus, on the western edge of what is now Turkey, there lived a philosopher named Heraclitus. He was a strange and solitary figure, known by his contemporaries as the weeping philosopher for his melancholy disposition, and as the obscure one for the deliberately riddling style of his writings. He came from a wealthy, aristocratic family, but reportedly renounced his inherited position to devote himself entirely to contemplation. He was said to have wandered the hills surrounding Ephesus, refusing to share his insights with those he considered unworthy, and to have eventually retreated into such deep seclusion that he developed an illness from his unconventional diet of plants and eventually died. Yet despite this reputation for difficulty and obscurity, Heraclitus left behind a handful of profound observations about reality that still echo through philosophy and physics to this day. His central insight was captured in a phrase that has become one of the most famous statements in all of Western thought. "No man," he declared, "ever steps into the same river twice, because the river is constantly flowing, constantly changing, always presenting new water in new configurations. And the man, too, is constantly changing, always a slightly different person than he was a moment before. The world," Heraclitus argued, "is not a collection of static things. It is a process. It is pure becoming. Everything flows," he said, "everything changes, and change itself is the only permanent feature of reality." For Heraclitus, time and change were essentially identical. The universe was fundamentally temporal, fundamentally dynamic, fundamentally in motion. The apparent stability of mountains, oceans, and stars was merely an illusion produced by changes occurring too slowly for human senses to easily perceive. At every scale, from the smallest to the largest, reality consisted of endless transformation. A cosmic fire perpetually burning, continuously remaking itself into new forms. Without change, without the river of time carrying everything forward, there could be no reality at all. Existence itself was defined by motion and transformation. Heraclitus used fire as a central metaphor for this dynamic reality. Fire, for him, was not merely one element among others, but a symbol of the perpetual transformation that he believed lay at the heart of all being. Just as fire consumes its fuel and transforms it into heat and light and ash, so does reality itself continuously consume its old forms and give birth to new ones. Nothing stays the same because nothing can stay the same. The very concept of a permanent, unchanging substance was, for Heraclitus, a confused fantasy invented by minds that could not bear to accept the true nature of the world. Life itself, he suggested, was a kind of slow burning, an ongoing combustion of materials gathered from the environment, transformed for a while into the patterns we recognize as living creatures, and eventually released back into the broader flux of existence. His writings, of which only fragments survive, are filled with paradoxes and riddles designed to jolt the reader out of complacent ways of thinking. "The way up and the way down are one and the same," he wrote, inviting us to see opposites as unified through their common participation in change. "Cold things warm up, warm things cool down, wet things dry, parched things become moist. Everything is constantly in the process of becoming its opposite, and this ceaseless transformation is not a defect in reality, but its very essence." To grasp reality truly, for Heraclitus, was to grasp this pervasive pattern of change, to see the unity of the process that connects what appears to be separate and opposed. But elsewhere in the Greek world, in the southern Italian city of Elea, another philosopher was reaching the exact opposite conclusion. His name was Parmenides, and he came of age in the generation following Heraclitus, probably born around the year 515 before the Common Era. Where Heraclitus had celebrated flux, Parmenides would deny it absolutely. Where Heraclitus saw becoming as the essence of reality, Parmenides would argue that becoming is impossible, that change is merely an illusion of the senses, and that the true nature of reality is eternal, unchanging, and completely outside of time. Parmenides presented his philosophy in the form of a philosophical poem, composed in the same heroic meter as the epics of Homer. In this poem, a goddess reveals to the philosopher the two possible ways of inquiry. The first is the way of truth, which leads to the conclusion that reality simply is, eternally and completely, without beginning or end or change. The second is the way of opinion, which follows the deceptive testimony of the senses and falsely believes in things coming into and going out of existence. Parmenides insisted that the first way was correct, and the second was a path that could not even be coherently investigated. His reasoning was austere and logical. For something to change, he argued, it must become something that it previously was not. But this would mean that it must come from nothing, and nothing cannot be the source of anything. Alternatively, it would mean that something ceases to exist and becomes nothing, but nothing cannot exist, and so nothing can become nothing. From these stark premises, Parmenides concluded that reality must be whole, complete, eternally itself, and fundamentally timeless. The appearance of change, of flow, of temporal passage, was nothing but a kind of cosmic optical illusion, a mistake made by beings who trusted their senses over their reason. What makes Parmenides so important in the history of thought is not just the radical nature of his conclusions, but the method he used to reach them. He did not rely on observation, because observation seemed to support the opposite view. He did not appeal to authority or tradition. Instead, he insisted on pure logical reasoning, starting from what he considered self-evident premises about being and non-being, and following the argument wherever it led, even when it led to conclusions wildly at odds with everyday experience. In this sense, Parmenides can be considered the first philosopher of science in the modern sense, the first thinker to place rigorous argument above the testimony of the senses. He was willing to believe that the entire world of change and becoming was an illusion because his logic told him it must be so. His student Zeno of Elea famously devised a series of paradoxes designed to support Parmenides' conclusions by showing that motion itself was logically impossible. If an arrow must travel half the distance to its target before reaching the target, and half of the remaining distance before covering that. And so on endlessly. Then the arrow can never actually reach its target, because there are infinitely many smaller distances to cross. If Achilles, the swift-footed Greek warrior, must first reach the point where the tortoise started before he can catch up with the tortoise, by which time the tortoise has moved a little further, then Achilles can never catch the tortoise, despite being much faster. These paradoxes were not meant as mere mathematical puzzles. They were intended as serious arguments that the world of motion and change was incoherent, that reality must fundamentally be the static, unchanging being that Parmenides had described. These two visions, radically opposed and yet strangely complementary, have structured Western thinking about time ever since. Every major debate in the physics and philosophy of time can be understood as a variation on the disagreement between Heraclitus and Parmenides. Is time real and fundamental, as Heraclitus would have it? Or is the appearance of time an illusion concealing a deeper, unchanging reality, as Parmenides argued? Is change the essence of existence, or is it merely a superficial feature that conscious minds project onto a fundamentally static universe? 2,500 years of subsequent philosophy, mathematics, and physics have not resolved this fundamental question. In fact, as we will see, modern physics has only made it more acute. Plato, the great systematizer of Greek philosophy, attempted to combine insights from both traditions. He proposed that there were two realms of reality. The higher realm of forms or ideas was eternal, perfect, and unchanging, very much like the being described by Parmenides. The lower realm of material objects and sensory experience was in constant flux, very much like the river of Heraclitus. For Plato, time itself belonged to this lower realm. He famously described time as a moving image of eternity, suggesting that the temporal world was a kind of inferior copy of a higher, timeless reality. The clock-like motions of the heavenly spheres, the sun, the moon, and planets, were the ultimate source of time for Plato, their regular revolutions providing the measure by which all other change could be tracked. Aristotle, Plato's most famous student, took a somewhat different approach. He argued that time could not exist without change, but also that time was not identical to change. Rather, time was the measure of change with respect to before and after. In other words, time required a mind capable of numbering the moments of motion. Without a conscious observer to count off the changes, could time really be said to exist at all? This was one of the first formulations of what we might now call a relational view of time. Time exists only in virtue of changes happening and being noticed. If nothing were happening, there would be no time. If there were no one to notice what was happening, perhaps there would also be no time in any meaningful sense. These ancient debates might seem like abstract intellectual exercises, distant from the concerns of modern science, but they set the terms for everything that came after. When Isaac Newton and Gottfried Leibniz would clash over the nature of space and time 1,500 years later, they would essentially be refighting the battle between Parmenides and Heraclitus, using the new tools of mathematics and mechanics. And when Albert Einstein would revolutionize our understanding of spacetime in the early 20th century, he would draw upon conceptual resources developed by those ancient Greeks, even if he did so unconsciously and through generations of intermediaries. The question of whether reality is fundamentally static or dynamic, whether time is real or illusory, whether matter and space require the presence of time or could exist without it, was already being debated on the rocky shores of the Mediterranean more than 2 millennia ago, and it has never really been resolved since. As the centuries rolled on and medieval philosophers wrestled with these ancient questions, primarily through the lens of Christian theology, they added their own complications. St. Augustine of Hippo, writing in the late 4th and early 5th centuries, struggled mightily with the nature of time. He penned one of the most famous passages about time ever written, confessing that he knew what time was when no one asked him. But when someone asked him to explain it, he found that he did not know. He wondered whether the past and future could really be said to exist at all, since the past was gone and the future had not yet arrived. Only the present, the infinitesimally thin slice of now, seemed to have any real existence. And yet Augustine also believed that God existed outside of time entirely, seeing all moments of history as a single eternal present. For God, there was no before and after, no flow, no change, just pure eternal being. It was a view strikingly similar to that of Parmenides, now dressed in theological rather than philosophical language. The scientific revolution of the 17th century inherited these ancient questions and transformed them utterly. The new mathematical physics that Galileo, Kepler, Descartes, and eventually Newton developed needed a precise framework in which to describe motion. And this meant formulating precise conceptions of space and time. The old philosophical debates now had to be translated into the hard-edged language of equations and measurements. And here, we encounter one of the most important intellectual controversies in the history of science: the titanic disagreement between Isaac Newton and Gottfried Wilhelm Leibniz over the very nature of space and time themselves. Isaac Newton, writing in his monumental work, the Principia Mathematica, published in 1687, laid out a view of space and time so clear and so consequential that it would dominate scientific thinking for more than 2 centuries. Newton's time was absolute. It was what he called true and mathematical time, flowing uniformly and equably without regard to anything external. Time, for Newton, was like a great cosmic river that carried all events along with it. It existed independently of the matter within the universe. Even if you somehow emptied the entire cosmos of every particle, every star, every galaxy, every speck of dust, time itself would continue to flow on, unchanged and unchanging, counting off its eternal seconds in a silent and empty void. Newton's space was similarly absolute. It was a vast, three-dimensional stage upon which the drama of the universe unfolded, possessing its own independent existence apart from any material objects it happened to contain. Space provided a universal reference frame against which absolute motion could be measured. An object was truly at rest or truly moving, not merely in relation to other objects, but in relation to absolute space itself. For Newton, both space and time were real, independent, pre-existing features of reality. The matter in the universe occupied them, but did not create them. If matter vanished, the stage would remain. Time would still tick. Space would still stretch infinitely in all directions, empty, but still absolutely, undeniably present. To defend this view, Newton offered his famous thought experiment of the rotating bucket. Imagine, he asked, a bucket of water suspended from a rope. If you spin the bucket, at first the water remains still while the bucket rotates around it. Eventually, friction drags the water into rotation as well, and the surface of the water becomes concave as centrifugal forces push it outward and up. Now, what is the water rotating relative to? Not the bucket, because at the moment when the water and the bucket are both spinning together, they are stationary relative to each other. Yet the water's surface is still concave, indicating that it is undergoing absolute rotation. Newton concluded that the water must be rotating with respect to absolute space itself, providing what he considered empirical evidence that such absolute space really existed. Newton's vision had a certain grand theological resonance as well. For Newton, who was a deeply religious man despite his unorthodox Christian views, absolute space was in some sense the divine sensorium, the medium in which God perceived all things. Absolute time was the flowing of God's own eternal duration. Space and time were not mere abstract concepts, but fundamental aspects of reality, imbued with almost sacred significance. To deny their absolute existence would be, in Newton's view, to undermine the very foundation upon which the regularity and lawfulness of the natural world ultimately rested. Without absolute space and time, how could there be true motion? How could the laws of nature apply uniformly throughout the cosmos? How could God oversee the operation of the universe from his position outside of it all? But across the English Channel, the German polymath Gottfried Wilhelm Leibniz was developing a radically different view. Leibniz was a relationist. He believed that space and time had no independent existence at all. Space, for Leibniz, was nothing more than the order of coexistence among material things. Time was nothing more than the order of succession among events. Without material things existing in various positions relative to each other, there would be no space. Without events happening in various orderings of before and after, there would be no time. Space and time were not containers. They were relationships. They were derivative features of matter, not fundamental aspects of reality in their own right. Leibniz was one of the greatest universal geniuses in the history of Western thought. He co-invented calculus independently of Newton, developed binary arithmetic that would eventually form the foundation of modern computing, made contributions to logic, metaphysics, theology, physics, history, and dozens of other fields, and served as a diplomat and librarian at various European courts throughout his career. His relationalism about space and time was part of a broader metaphysical vision in which the fundamental constituents of reality were not extended physical objects at all, but rather what he called monads, indivisible spiritual units that perceived and expressed the entire universe from their own particular perspectives. For Leibniz, the physical world of extended bodies moving through space and time was, in a sense, derivative, a phenomenal expression of the deeper reality of these monadic perspectives on one another. Space and time, being features of the physical world, were therefore not fundamental, but emerged from the relationships among the more basic monadic realities. The debate between Leibniz and Newton's defender Samuel Clarke, conducted through a famous series of letters, exchanged between 1715 and 1716, represents one of the most important philosophical correspondences in the history of Western thought. Leibniz argued that Newton's absolute space and time violated two fundamental principles of rational inquiry. The first was the principle of sufficient reason, which held that there must always be a reason for things being as they are rather than otherwise. If absolute space existed, Leibniz asked, why would God have created the universe in this particular part of it rather than some other? If every location in absolute space is indistinguishable from every other, then there could be no sufficient reason for the choice, and hence, absolute space could not exist. The second was the principle of the identity of indiscernibles, which held that two things that are in every way identical must in fact be the same thing. If you could shift the entire universe 10 feet to the left in absolute space, nothing observable would change. The two universes would be indiscernible. Therefore, by Leibniz's logic, they must actually be the same universe, meaning that absolute location in space has no real meaning. Leibniz made parallel arguments about time. If absolute time existed independently of events, then why did God create the universe at the moment he did, rather than some earlier or later moment? If every moment of absolute time is identical to every other, there could be no reason for the choice. And so absolute time, Leibniz concluded, must be an incoherent concept. Time, properly understood, was just the ordering of events. Without events, there was no time. The debate was never formally resolved, and indeed, both thinkers died within a few years of writing their famous letters. But for the next 2 centuries, Newton's view dominated. His physics was spectacularly successful in explaining the motions of planets, the trajectories of projectiles, and the tides of the oceans. His absolute space and absolute time seemed to be working assumptions that yielded correct predictions about the physical world. Leibniz's relationalism, while philosophically appealing to many, appeared to lack the empirical backing needed to dethrone Newtonian orthodoxy, and yet cracks in the Newtonian edifice began to appear. In the late 19th century, the Austrian physicist and philosopher Ernst Mach took up the Leibnizian torch and argued that Newton's bucket experiment did not actually demonstrate the existence of absolute space. According to Mach, when the water in the bucket rotates, it is rotating relative to the distant stars and galaxies, the combined matter of the entire universe. If you could somehow remove all the other matter in the cosmos and leave only the bucket, Mach argued, the water's surface would not become concave when you spun it. Rotation, and indeed all inertial effects, would be meaningless in an empty universe. This position, known as Mach's principle, would have a profound influence on one particular young man working as a patent clerk in Switzerland at the turn of the 20th century. That young man was Albert Einstein, and in the year 1905, he would begin a scientific revolution that would transform our understanding of space and time forever. Working in his spare moments while reviewing patent applications, Einstein developed what would come to be called the special theory of relativity, building on earlier insights from James Clerk Maxwell's theory of electromagnetism, and the realization that the speed of light was the same for all observers regardless of their motion. Einstein derived a series of conclusions that would have seemed utterly impossible just a few years earlier. Moving clocks run slowly. Moving objects contract in their direction of motion. 2 events that are simultaneous for one observer are not simultaneous for another observer, moving relative to the first. The flow of time, it turned out, was not universal and absolute as Newton had claimed. Time itself depended on the observer. The implications of this were staggering. Consider 2 observers, one on a spacecraft traveling at great speed past Earth, another standing on the ground watching the spacecraft pass. Both observers see their own clocks ticking at the normal rate, and each sees the other's clock running slow. This is not an illusion or a perceptual trick. It is a genuine feature of reality. There simply is no fact of the matter about whose clock is really running at the correct rate. Each observer is perfectly justified in regarding their own clock as the true measure of time, and the other observer's clock as being the slow one. The familiar Newtonian notion of a single universal time flowing at the same rate for everyone, everywhere, simply collapsed in the face of these results. There were as many times as there were observers, each valid in its own frame of reference, none more fundamental than the others. Even more disturbing was the question of simultaneity. In Newton's physics, there was always a definite fact about whether two events happened at the same moment. Either they did or they did not, and all observers would agree. But in Einstein's relativity, observers moving relative to each other could genuinely disagree about whether two events were simultaneous. Worse still, observers could disagree about which event came first. There were circumstances where one observer would see event A happening before event B, while another observer moving in a different direction would see event B happening before event A. Neither observer would be wrong. Both descriptions would be equally valid according to the physics of special relativity. The notion of an objective temporal ordering of distant events simply did not survive the new theory. But Einstein was not finished. His former mathematics professor, Hermann Minkowski, who had once called the young Einstein a lazy dog in his classes, now took his former student's work and gave it a startling geometrical reformulation. Space and time, Minkowski announced in a famous speech in 1908, were not independent entities at all. They were merely two facets of a single unified four-dimensional continuum, which he called spacetime. Space alone and time alone, he declared, were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. This was a profound shift. Time was no longer a separate dimension flowing apart from space. Time was literally just another direction in a four-dimensional geometric manifold, albeit a direction with peculiar mathematical properties. Einstein embraced Minkowski's geometric formulation and used it as the foundation for an even more radical development. In 1915, after nearly a decade of intense mathematical struggle, Einstein unveiled his general theory of relativity. In this new theory, spacetime was not merely a passive stage on which matter performed its motions. Spacetime was itself dynamic, a kind of flexible fabric that could be warped and curved by the presence of mass and energy. What we call gravity was not a mysterious force acting at a distance, as Newton had thought. Gravity was simply the curvature of spacetime. Massive objects bent the geometry of space and time around them, and other objects moved along the resulting curved paths in what looked to us like gravitational attraction. This was an extraordinary synthesis. It meant that space and time were not absolute, as Newton had believed, but neither were they purely relational, as Leibniz had argued. In general relativity, spacetime has its own dynamics, its own equations of motion, its own real physical properties. And yet those properties are inextricably bound up with the matter and energy that fill spacetime. Matter tells spacetime how to curve, in the famous summary offered by the physicist John Archibald Wheeler, and spacetime tells matter how to move. Neither side of this equation makes sense without the other. Space, time, and matter form a single tightly interconnected whole. Einstein himself was strongly influenced by Machian ideas in developing general relativity, and at one point, he believed his theory had fully implemented Mach's principle of pure relationalism. Later analyses would show this to be only partially true. General relativity does permit solutions describing completely empty universes that still have a well-defined spacetime geometry, suggesting that spacetime has some independent existence apart from matter. On the other hand, the presence of matter fundamentally shapes spacetime, and there are deep questions about whether spacetime without matter really has any physical meaning. Perhaps more importantly for our central question, Einstein's relativity did something profound to our conception of time itself. In the old Newtonian picture, time was a universal river flowing at the same rate everywhere. In Einstein's picture, There was no such universal river. Every observer, every object, had its own proper time, ticking according to its own particular trajectory through space-time. A clock carried by an astronaut orbiting Earth runs measurably slower than an identical clock left on the ground. Because the two clocks follow different paths through the curved space-time surrounding our planet, these tiny differences have been confirmed by countless experiments and must be corrected for in the operation of satellite-based navigation systems, which would be useless within hours if general relativistic time corrections were not applied. Even more disturbing was the fact that general relativity eliminated any universal notion of the present. In Newtonian physics, the present was the same everywhere. Right now, at this very instant, there is a definite state of the universe. But in general relativity, different observers in relative motion to each other have genuinely different perspectives. Events that are simultaneous for you may not be simultaneous for someone flying past you in a spaceship. The notion of now turned out to be observer-dependent and fundamentally local. There was no universal now flowing across the entire cosmos. Many physicists and philosophers have interpreted this as strong support for what is called the block universe view, according to which all moments of time are equally real, just as all points in space are equally real. The past, the present, and the future all coexist in a single four-dimensional geometric structure. And our sense of time flowing is a kind of illusion produced by our limited conscious perspective within the block. If this view is correct, then time in any meaningful sense may not exist at all. There is no flow. There is no passage. There is just the unchanging geometric structure of space-time, with all events eternally arranged in their fixed relationships to one another. You at age 5, you at age 50, you on the day you will eventually die. All of these yous exist equally and forever within the block. The sense that one of them is the real you while the others are somehow less real is, according to the block universe view, nothing more than a perspective effect, a peculiar feature of conscious experience that does not correspond to any fundamental feature of reality. But even as relativity was demolishing the Newtonian conception of absolute time, another revolution was brewing that would complicate matters even further. Quantum mechanics, the strange and counterintuitive theory describing the behavior of matter at the smallest scales, had emerged alongside relativity in the early 20th century, and quantum mechanics had its own peculiar relationship with time, one that turned out to be fundamentally incompatible with the way time appeared in relativity. Reconciling these two great theories of physics, general relativity and quantum mechanics, would become one of the greatest challenges of 20th and 21st century theoretical physics. And strikingly, the most serious attempts to unify them all seem to lead to the same shocking conclusion. Time, as we understand it, may not be a fundamental feature of reality at all. Before we plunge into that quantum abyss, though, we need to confront another aspect of time that has puzzled physicists for generations. Namely, why does time seem to have a direction? Why does the past differ so dramatically from the future? Why do eggs break but never unbreak? Cups shatter but never reassemble? Memories form of yesterday but never of tomorrow? If the equations of physics treat time symmetrically, what is it that makes time appear to flow inexorably in one direction? The answer, as developed by physicists in the 19th century and refined ever since, has to do with a quantity called entropy. Entropy, roughly speaking, is a measure of disorder, or more precisely, a measure of the number of microscopic arrangements that correspond to a given macroscopic state. The second law of thermodynamics, one of the most solidly established principles in all of science, states that the entropy of an isolated system tends to increase over time. In a closed system, disorder grows. Heat flows from hot objects to cold ones, not the other way around. A drop of ink spreads out through a glass of water and does not spontaneously reassemble itself into a drop. This irreversible tendency gives time its apparent direction, which the physicist Arthur Eddington famously named the arrow of time. Consider a simple example. Imagine a deck of cards, perfectly ordered by suit and rank. This is a highly organized, low-entropy configuration. Now shuffle the deck thoroughly. The cards will end up in some jumbled arrangement, a high-entropy configuration. The reason for this is not that any particular disordered arrangement is more physically favored than the ordered one. In fact, every specific arrangement is equally probable when you shuffle. The reason is that there is only one completely ordered arrangement, while there are astronomically many disordered arrangements. So when you shuffle, you are overwhelmingly likely to end up in one of the many disordered states, rather than the single, ordered one. This is the statistical origin of the second law. Systems tend toward higher entropy, not because of any deep physical preference, but simply because higher entropy states are vastly more numerous. Now apply this to the entire universe. The second law says that the total entropy of the cosmos must be increasing. Galaxies form, stars burn, heat flows outward, and the overall disorder grows. But this raises an absolutely crucial question. Why was the universe in such a low entropy state in the first place? If high entropy configurations are so much more common, why did the universe begin in one of those extraordinarily rare low entropy arrangements? This puzzle is sometimes called the problem of the past hypothesis, and it remains one of the deepest unsolved mysteries in cosmology. Roger Penrose has estimated that the initial low entropy state of the universe was so special, so improbable, that its probability was something like 1 in 10 to the power of 10 to the power of 123. A number so large that it defies ordinary comprehension. To appreciate just how extraordinary this low entropy beginning is, consider that if you took the total observable universe, with all its stars and galaxies and matter, and randomly reshuffled it into any possible configuration, the chances of ending up with something resembling our actual early universe are smaller than the chances of any other specific outcome you might imagine. It is the ultimate cosmic coincidence. Some physicists have suggested that this improbable initial state must be taken as a fundamental postulate of cosmology, a brute fact that cannot be further explained. Others have proposed that the apparent low entropy is a selection effect, that observers can only exist in regions of the universe where entropy started low and is increasing. Because the formation of complex structures like galaxies, stars, planets, and brains requires the kind of temperature gradients and free energy flows that only exist in a universe evolving from low entropy toward higher entropy. In a universe already at maximum entropy, there would be no way for anything interesting to happen, no way for life or consciousness to emerge, no observers to wonder about the absence of temporal flow. The connection between entropy and time was first clearly articulated by the astrophysicist Arthur Eddington in the 1920s. Eddington coined the phrase arrow of time to capture this strange asymmetry. The fundamental laws of physics, he noted, do not distinguish between past and future. If you recorded the motion of individual particles and then played the recording backward, you would not be able to tell from the particles' behavior which direction was the correct forward direction in time. The laws are time-symmetric, and yet, at the macroscopic scale, time is dramatically asymmetric. We remember the past, but not the future. We can affect the future, but not the past. Things age, deteriorate, and fall apart, but they do not spontaneously become younger or more ordered. This asymmetry must come from somewhere, and the overwhelming consensus among physicists is that it comes from the second law of thermodynamics, which in turn comes from the peculiar low entropy beginning of the universe. What does all this have to do with our question about whether space and matter can exist without time? Rather a lot, actually. Because the arrow of time, the direction in which time flows, seems to be deeply connected to the second law of thermodynamics, and the second law in turn depends on the special low entropy initial conditions of the universe. If the universe had not started out in such an improbable ordered state, there would be no directionality to time. Every process would be reversible. Past and future would be indistinguishable. The very concept of flowing time, of change happening, of anything ever actually occurring rather than just statically being, would lose its meaning. This suggests that what we experience as time, the flowing forward, the ever-growing past, and the open future, may not be a feature of the fundamental equations of physics at all. It may be an emergent phenomenon, arising specifically because the universe started in such an unusual low-entropy state and is evolving toward higher entropy configurations. The deep laws of nature might be fundamentally timeless, symmetric, and reversible. Time's apparent passage might be nothing more than a statistical consequence of the particular starting conditions we happen to have been given. This is a view strongly championed by physicists like Sean Carroll, who has argued that the arrow of time emerges purely from the low entropy of the early universe and has nothing to do with time itself being fundamentally directional. If this is correct, then we can imagine a universe that started in a maximum entropy state and has simply remained there forever. In such a universe, there would be no flow of time, no before and after, no change of any kind. Matter and space could still exist in some abstract sense, arranged in whatever configuration they happen to be arranged in. But without the ordering provided by entropy increase, there would be no way to say which configuration came first or last. Time would have no meaning. The universe would be frozen, not because time was stopped, but because time had no basis on which to exist. Space and matter would remain, but time, the thing we usually think of as the flowing dimension that ties it all together, simply would not be there. Now we arrive at what is perhaps the most startling and counterintuitive piece of the entire puzzle. The place where modern theoretical physics most directly challenges our assumption that time must be a fundamental ingredient of reality. This is the notorious problem of time in quantum gravity, which emerges from attempts to unify general relativity with quantum mechanics. And at the center of it all stands one of the strangest equations ever written down, an equation that describes the wave function of the entire universe, and that, remarkably, contains no time variable at all. The story begins in 1965, at an unlikely location. The physicist John Archibald Wheeler, one of the great theoretical minds of the 20th century, and the man who had given black holes and wormholes their modern names, found himself with a 2-hour layover at the Raleigh-Durham Airport in North Carolina. He was on his way to somewhere else, but decided to use the time productively by inviting his colleague Bryce DeWitt, a physicist at the nearby University of North Carolina, to meet him at the airport. DeWitt arrived with a fresh piece of mathematics in mind. He had been thinking about how to quantize gravity, how to combine Einstein's classical theory of general relativity with the principles of quantum mechanics, and he proposed to Wheeler something that neither of them fully realized the implications of at the time. The idea was to apply to gravity the same procedure that had been used to develop quantum mechanics for the hydrogen atom decades earlier. In quantum mechanics, you take a classical equation describing the energy of a system and convert it into a wave equation describing the quantum state of that system. Apply this to the equations of general relativity, and you get a wave equation for the universe itself, a quantum description of the entire cosmos. Wheeler became enormously excited by this idea and declared on the spot that the equation for quantum gravity had been found. It would come to be known as the Wheeler-DeWitt equation, though both men would later express some reservations about the rushed nature of its discovery. To understand why this equation came to have such strange properties, we need to appreciate something subtle about how general relativity treats time. In Einstein's theory, time is not a separate ingredient added to physics from the outside. Time is built into the very geometry of spacetime. And crucially, the equations of general relativity possess a peculiar kind of symmetry called time diffeomorphism invariance, which essentially says that the physics does not care about how you label the time coordinate. You can relabel time any way you like, using any monotonic function, and the physics stays the same. This is a remarkable property, and it captures something deep about relativity, namely that there is no preferred universal time. But this same property has a shocking consequence when you try to quantize the theory. The time diffeomorphism invariance becomes a constraint on the quantum states, a condition that must be satisfied by any valid wave function of the universe. And when you work out the mathematics carefully, this constraint takes the form of an equation saying that the Hamiltonian, which in ordinary quantum mechanics would give you the energy and drive the time evolution of the system, instead gives you zero when applied to the wave function of the universe. This is what is meant by saying the Wheeler-DeWitt equation contains no time. The equation is telling us that, at the level of the entire universe, there is no evolution in time because time itself has dissolved into the background geometry. But when physicists actually began to examine this equation, they noticed something profoundly disturbing. The equation had no time variable in it at all. The Wheeler-DeWitt equation is a constraint equation that says, in essence, that when the Hamiltonian operator acts on the wave function of the universe, the result is zero. Unlike the ordinary Schrödinger equation of quantum mechanics, which describes how a wave function evolves in time, the Wheeler-DeWitt equation describes a static wave function that does not evolve at all. There is no time parameter. There is no evolution. The universe, according to this equation, is a frozen, static, eternal thing, neither changing nor failing to change, simply existing in a timeless state of being. This is the problem of time in quantum gravity, and it has been called one of the deepest conceptual puzzles in all of theoretical physics. How can we reconcile an equation describing a timeless universe with our overwhelming experience of time passing, of things changing, of history unfolding moment by moment? Different physicists have taken different approaches to this problem. Some have tried to find hidden time variables within the equation, suggesting that time might be encoded in some feature of the wave function, even if it is not explicit. Others have argued that the Wheeler-DeWitt equation is simply incomplete, that we are missing something essential that would reintroduce time when we get the theory right. Still, others have embraced the apparent timelessness of the equation and suggested that it is telling us something profound about the true nature of reality. Namely, that time is not a fundamental feature of the universe at all. Perhaps the most famous champion of this last view is the British physicist Julian Barbour, whose 1999 book, The End of Time, made a provocative case that time simply does not exist, that our entire experience of temporal flow is a kind of persistent illusion produced by a universe that is actually completely static. Barbour's path to this radical conclusion was unusual. After completing his doctorate at the University of Cologne in 1968 on the foundations of general relativity, he never took a conventional academic position. Instead, he supported himself and his family by working part-time as a translator of Russian scientific articles, giving him the freedom to pursue his unconventional research interests on his own terms. For decades, he worked in relative obscurity, developing his ideas in a farmhouse near Banbury in England, communicating with a small circle of fellow travelers who shared his interest in timeless physics. Barbour's vision is genuinely radical. He proposes that the universe is not a thing that exists in time, but rather a vast collection of timeless instants, each one a complete snapshot of everything that exists, each one eternal and unchanging in its own right. He calls this collection Platonia, in honor of Plato's realm of eternal forms. Every possible configuration of matter and space, every possible arrangement of particles and fields, exists somewhere in Platonia. These configurations do not follow one another in a sequence. They simply are, all equally real, all equally eternal, all equally present in this vast landscape of possibilities. What we experience as the flow of time, according to Barbour, is actually our consciousness moving, in some sense, across this landscape, encountering different instants, and stitching them together in our minds into the illusion of continuous temporal experience. To understand Barbour's picture, imagine a deck of infinitely many photographs, each one a perfectly detailed snapshot of some possible arrangement of the entire universe. One photograph might show the Big Bang in its earliest moments. Another might show our Milky Way galaxy forming. Another might show you reading these words right now. Another might show a universe full of nothing but empty space and scattered radiation, trillions of years from what we call now. Each photograph is complete in itself. None of them is connected to any other by any flow or passage of time. They simply exist, all at once, eternally, in a realm where time has no meaning. When we experience what we call the passage of time, we are, in Barbour's view, experiencing some kind of movement through this landscape of photographs, encountering them in a particular ordering that makes them seem connected into a coherent story. But here is the truly mind-bending part of Barbour's theory. Nothing in his model actually explains why we experience this particular ordering rather than some other, or why we experience any ordering at all. The landscape of Platonia is fundamentally timeless and has no intrinsic ordering. Yet somehow, from within this timeless structure, conscious beings like us emerge with the impression of progressing through time. Barbour attempts to explain this by pointing to the mathematical structure of the configuration space, arguing that certain special configurations, which he calls time capsules, have the property of containing within themselves apparent records of other configurations, records that look like memories of a past or traces of events that have happened. These time capsules are not genuine records of actual historical events. They are eternal features of particular points in Platonia that happen to have the structure of what a record would look like if there really were a temporal history. Our brains, Barbour suggests, are the most elaborate time capsules imaginable, encoding within their neural patterns what seem to be detailed memories of personal histories that, in his view, never actually happened in any fundamental sense. The physics that supports Barber's vision comes from a careful analysis of both general relativity and quantum mechanics when they are properly formulated in a fully relational way, stripped of any absolute background time. In such formulations, what remains is essentially a static configuration space with a wave function spread across it. Some configurations are more likely than others in a probabilistic sense, and remarkably, the configurations that are most probable tend to be those that appear to contain records of other configurations, as if each instant carried within it traces of a past that never actually existed as a separate thing. Barber calls these special configurations time capsules. They are not snapshots of a history that actually happened. They are static patterns that look as if they are snapshots of history, despite being simply eternal features of a timeless reality. If Barber is right, then the question of whether space and matter can exist without time has a surprisingly direct answer. Not only can they exist without time, they actually do. The apparent temporal dimension of our experience is an illusion. Reality consists of eternal, timeless configurations, and time itself is simply a psychological feature of how conscious beings interpret these configurations. Space is real, matter is real, but time, in any fundamental sense, is not. Of course, not everyone accepts Barber's view. The physicist Lee Smolin, a prominent theoretical physicist who has worked with Barber over the years on relational physics, nevertheless strongly disagrees with Barber's timelessness conclusion. For Smolin, time is real and fundamental, not emergent or illusory. He has argued that the confusion between timeless mathematical models and actual physical reality has led physicists astray. The equations of physics are timeless, Smolin admits, but that does not mean the world they describe is timeless. Smolin worries that eliminating time from our picture of reality makes it impossible to understand genuine change, novelty, or causation. The physicist Sean Carroll, while open to the idea of timelessness, has expressed skepticism about what exactly is gained by it. He has pointed out that even if we accept that the fundamental equations of physics do not contain a time variable, we still need to explain why our experience seems so overwhelmingly temporal. What is the value of the timeless perspective if it does not ultimately connect back to the reality we actually inhabit? These are legitimate concerns, and they remind us that the question of time in physics is not simply settled. It remains one of the most actively debated topics in the foundations of physics. Another approach to understanding the timelessness of quantum gravity comes from the Italian physicist Carlo Rovelli, one of the founders of an approach called loop quantum gravity. Rovelli has become something of a public intellectual in recent years, author of best-selling popular science books, including 7 Brief Lessons on Physics and The Order of Time, the latter of which outsold even 50 Shades of Grey in his native Italy. Rovelli's vision of time is nuanced and subtle, and it combines elements of both the timeless and temporal views. In loop quantum gravity, space itself is not continuous, but is built up from discrete quanta, tiny indivisible units sometimes called atoms of space. These atoms form networks known as spin networks, with nodes representing the atoms and links connecting them. The dynamics of the theory are captured not by evolution in time, but by how these spin networks transform into one another through discrete local moves. Crucially, there is no overarching time parameter governing this evolution. The theory is fundamentally background independent and does not require any pre-existing notion of time. Ravelli's view is that time, in a certain sense, does not exist at the fundamental level. When he writes that time does not exist, however, he is making a carefully qualified claim. He is not saying that change does not happen, or that the universe is static in some barbarian sense. Rather, he is saying that there is no universal time variable in the fundamental equations, no cosmic clock ticking at the same rate everywhere, no absolute notion of simultaneous events across the universe. At the most fundamental level, reality consists of quantum events, discrete happenings at the tiniest scales, and these events do not fit into a single unified temporal order. Instead, time emerges out of the relationships between events, out of the interactions between different parts of the universe. Ravelli has sometimes compared time to temperature. A single molecule does not have a temperature. Temperature is a statistical property that emerges only when you have a large collection of molecules interacting with each other. In a similar way, he argues, a single quantum event does not have a time associated with it. Time emerges only statistically, at the level of large collections of events interacting in particular ways. Our experience of time flowing, for Ravelli, is a consequence of our being part of a complex macroscopic system in which temporal ordering makes sense as a useful approximation, even though it is not a fundamental feature of the underlying reality. This analogy is illuminating because it reminds us that emergent properties can be extremely robust, extremely useful, and even essential to how we describe certain phenomena without being fundamental. Temperature is not an illusion. It is a real feature of thermodynamic systems, but it does not exist at the level of individual particles. It exists only when you zoom out and consider collections of particles in thermal equilibrium. Similarly, time might be perfectly real at the scales we normally inhabit, while simply not existing at the fundamental quantum gravitational level. The question of whether time is real or illusory might be the wrong question to ask. The right question might be, at what scales does time make sense, and what underlies it at deeper scales where it does not? Together with the mathematician Elaine Kahns, Ravelli has developed what is called the thermal time hypothesis, which suggests that the time we experience is essentially a thermodynamic phenomenon. When a system is in thermal equilibrium, it has a natural notion of time associated with it, derived from the statistical distribution of its microscopic states. Our macroscopic experience of time might be nothing more than this thermal time, emerging out of our incomplete knowledge of the detailed microscopic state of the universe. From this perspective, time is not an illusion exactly, but it is not fundamental either. It is a useful emergent concept, like temperature or pressure, that makes sense at certain scales, but loses its meaning when you zoom in to the quantum gravitational level. The thermal time hypothesis has several attractive features. It connects the mystery of time's apparent flow with the well-understood mathematical framework of statistical mechanics. It provides a natural explanation for why time seems to have a direction. Since thermal systems naturally evolve toward equilibrium in ways that distinguish past from future, and it offers a path toward reconciling the timelessness of general relativity at the fundamental level with the very real temporal experience we have in our daily lives. Whether or not the details of the hypothesis will ultimately prove correct, it represents one of the more creative attempts to understand how time can be simultaneously fundamental to our experience and absent from our deepest equations of physics. These ideas from loop quantum gravity point toward an even more remarkable possibility. That time might emerge not just from thermodynamic or statistical considerations, but from quantum entanglement itself, from the deepest layer of quantum correlations between different parts of the universe. This idea originated in a paper published in 1983 by the physicists Don Page and William Wouters, and it has recently received striking experimental support. Page and Wouters proposed a way to reconcile the timelessness of the Wheeler-DeWitt equation with our experience of time passing. Their idea is elegant and profound. Imagine the universe divided into two parts, a clock and everything else. The clock could be anything that has a well-defined quantum state that correlates with time. For example, a rotating object, an oscillating field, or simply another quantum system whose state changes in a predictable way. The rest of the universe they called the system. Now, crucially, Page and Wouters proposed that the clock and the system are entangled, meaning that their quantum states are correlated in a specific quantum mechanical way. An external observer looking at the combined clock and system would see nothing evolving. The total state would be perfectly static, exactly as the Wheeler-DeWitt equation predicts. But an internal observer, someone embedded within the universe who can only see the system relative to the clock, would experience the system as evolving in time, with the clock playing the role of a time variable. In this framework, time is not a fundamental feature of reality. Time is a relational phenomenon that emerges from quantum entanglement between different parts of the universe. The universe as a whole is static, but from the perspective of any observer inside it, things appear to evolve because the observer is entangled with the rest of the cosmos in ways that make temporal evolution an inevitable feature of their experience. For decades, the Page and Wouters mechanism remained a theoretical curiosity, an interesting but unproven idea that might or might not reflect how the universe actually works. But in 2013, a team of researchers led by Ekaterina Morva carried out an experiment that provided remarkable empirical support for the mechanism, using entangled photons, with one photon serving as a clock and another as the system. They set up an experimental configuration that allowed them to compare the perspective of an internal observer, entangled with the clock, to that of an external observer who looked at the combined system from the outside. The results confirmed the predictions of Page and Wouters. The internal observer saw the system evolving in time. The external observer saw nothing changing at all. Time really did seem to emerge out of quantum correlations, at least in this experimental simulation of the universe. The Morva experiment used the polarization states of entangled photons to encode the quantum information needed to test the mechanism. Imagine two photons whose polarizations are quantum mechanically correlated in such a way that they share a single entangled state. One of these photons is designated as the clock, with its polarization serving as the timekeeping variable. The other photon is the system whose evolution is to be measured. An internal observer in this setup can measure the system conditional on measuring the clock in a particular state, effectively correlating themselves with the clock, and thereby gaining access to a time variable. An external observer, by contrast, measures only global properties of the combined two-photon state and sees no evolution at all. The experiment is a kind of miniature model of the Page-Wouters picture of the universe, and it worked exactly as the theory predicted. Time, in this experimental setup, really was a relational feature that emerged when the right kind of entanglement was in play. What is so striking about this line of research is that it provides a concrete, testable, physical realization of an idea that had seemed purely philosophical or theoretical. If you can simulate in the laboratory a miniature universe in which time emerges from entanglement, it is far harder to dismiss the idea as mere abstraction. The work suggests that time might genuinely be an emergent phenomenon at the deepest level, that what we call the flow of time is nothing more than the unfolding of quantum correlations between different subsystems of a fundamentally static whole. The universe at the deepest level might be the static entangled state that the Wheeler-DeWitt equation describes, while the time we experience is what appears when we, as internal observers, become entangled with some subset of the universe that serves as our clock. More recent work by Alessandro Capo and collaborators, published in Nature Communications in 2021, has extended these ideas significantly. They showed that the Page and Wouter's mechanism can be smoothly connected to classical physics through the use of something called generalized coherent states. In the appropriate limits, the entanglement-based emergent time reproduces the ordinary time of classical mechanics, complete with the familiar Schrödinger equation of quantum mechanics and the Hamilton equations of classical mechanics. Most strikingly, their work suggests that there is no such thing as quantum time versus classical time. There is only one time, and it is fundamentally a manifestation of entanglement between different parts of the universe. Even more recent research, including work by Tommaso Favalli and colleagues at the University of Naples, has extended these ideas to include not just time, but space as well. By applying similar techniques to a globally timeless and positionless universe, they have shown that both time and spatial relationships can emerge out of quantum entanglement among subsystems. Their models reproduce key features of general relativity, including the time dilation effects predicted by the Schwarzschild solution for gravitational time dilation around a massive body. This is a stunning result. It suggests that not only time, but space itself might be emergent phenomena, arising from quantum correlations in a universe that fundamentally lacks any spatial or temporal structure at its deepest level. If this picture is correct, then the answer to whether space and matter can exist without time becomes quite interesting. The question may be based on a false premise. Perhaps neither space nor time is fundamental. Perhaps they are both emergent, derivative properties that appear only when certain patterns of quantum entanglement exist among the various parts of the universe. Matter in the form of quantum information, of qubits and their correlations, might be the truly fundamental thing. Space and time might be the stage that this quantum matter constructs for itself through its patterns of mutual connection. Without the matter to entangle, there would be no space and no time. Without space and time, the matter would exist only as pure abstract quantum information, unstructured by any geometric framework. This picture also has remarkable implications for one of the oldest questions about the nature of reality, namely, what came before the Big Bang. In conventional cosmology, the Big Bang is often described as the beginning of time itself. Before the Big Bang, there was no time, because time itself began with the explosion. Asking what happened before the Big Bang is like asking what lies north of the North Pole, as Stephen Hawking famously put it. It is a meaningless question because the concept being invoked does not apply. But if time is emergent rather than fundamental, this picture becomes more complicated. The Big Bang may not be the beginning of time in any absolute sense. It may instead be the moment when time began to emerge, when the patterns of quantum entanglement in the universe began to support something that could be described as temporal evolution. Before that moment, in whatever sense before can be applied, there might have been some sort of prior state of reality, a quantum state that lacked the particular entanglement structure needed to support time, but that nevertheless existed in some abstract sense. In 2025, a significant survey of leading physicists conducted by Phil Halper and colleagues revealed a remarkable shift in thinking within the field. The Big Bang, according to most surveyed physicists, is no longer viewed as the absolute beginning of time. Instead, most researchers now distinguish between the hot Big Bang, which refers to the early hot, dense state of the universe that is well supported by observational evidence, like the cosmic microwave background, and the Big Bang singularity, which refers to the hypothetical moment of infinite density at time zero, predicted by the classical equations of general relativity. The latter is increasingly viewed as a mathematical artifact of our classical theory, rather than a physical reality. And most physicists now believe that some kind of physical process or prior state, likely preceded what we call the beginning of our universe. Physicists have proposed a variety of scenarios for what such a pretemporal state might have looked like. The Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in the 1980s, suggests that if you trace the universe backward in time toward the Big Bang, time itself smoothly transitions into an additional dimension of space. At the earliest moments of the universe, there was no distinction between time and space. Only as the universe evolved did this distinction emerge, giving rise to the temporal dimension we now experience. In this picture, asking what happened before the Big Bang really is meaningless, but not because there was nothing before, just because there was no before, because the concept of time had not yet emerged to make such a question sensible. Other proposals describe cyclical or bouncing universes, in which the Big Bang was not the beginning at all, but rather a transition from a previous phase of the universe, perhaps one that was contracting before it rebounded into expansion. Loop quantum cosmology, an application of loop quantum gravity to cosmological models, suggests that the initial singularity of the Big Bang is replaced by a big bounce, with our expanding universe emerging from the collapse of a previous universe. Some versions of string theory suggest that our universe is one of many that emerge through collisions of higher dimensional structures called branes. In all of these scenarios, time in some form may have existed long before what we conventionally call the beginning of our universe. A particularly intriguing proposal comes from the Canadian physicist Neil Turok and his colleagues, who have developed what they call the CPT-symmetric universe model. In this scenario, our universe and a mirror anti-universe emerged simultaneously from the Big Bang, with the anti-universe running backward in time from our perspective. The two universes would together constitute a complete CPT-symmetric whole, with charge conjugation, parity reversal, and time reversal all mapping one universe onto the other. The model has some attractive features, including potentially explaining certain features of the cosmic microwave background, but it remains highly speculative. Other physicists, like Sean Carroll and Jennifer Chen, have proposed scenarios where our universe emerged from a much larger and older multiverse, potentially one that had existed in some sense forever, with what we call the beginning of time simply being the emergence of our particular bubble from this eternal backdrop. And there is an even stranger possibility, pursued by the physicist Roger Penrose in his conformal cyclic cosmology. Penrose suggests that when the universe reaches its ultimate far future state, a cold, dilute, expanding void in which all the stars have burned out and all the black holes have evaporated, time in a meaningful sense effectively ends. There are no processes happening, no events, no way to mark the passage of time. And in this timeless state, which he calls the remote future, the universe becomes mathematically equivalent to another Big Bang. The end of one cosmic cycle becomes the beginning of the next, connected by a transition through a fundamentally timeless intermediate state. The universe, in this view, is an endless chain of cycles, connected by moments of timelessness in which space and matter continue to exist in some form, even though there is no time at all. What all of these ideas have in common is the recognition that time, far from being the universal unchanging background that Newton assumed, is something subtle, elusive, and possibly derivative. Time might be an emergent phenomenon. Time might be an illusion produced by the specific ways conscious observers interact with the universe. Time might exist robustly at some scales, but disappear at others. Time might have a beginning, an end, or both, or neither, depending on which theoretical framework you adopt. And running through all of this is the persistent, unsettling possibility that space and matter might indeed be able to exist without time, at least in some fundamental sense, even if the universe we actually inhabit happens to include time as an emergent feature of its structure. Let us return to our original thought experiment, the frozen universe in which everything has come to a complete stop. We can now see that this thought experiment is not just a philosophical curiosity, but something that maps onto serious physical possibilities. If time is emergent rather than fundamental, then a universe without time is not a logical impossibility. It is a coherent possibility that physics allows us to contemplate seriously. Whether or not our universe has ever actually been in such a state, or will ever be in such a state, is a separate question. But the conceptual possibility is real, and it has profound implications for how we think about existence itself. Consider what it would mean for our universe to be fundamentally timeless. Every moment of history, every event from the Big Bang to the eventual heat death of the cosmos, every birth and every death, every joy and every sorrow, all of these would exist eternally and simultaneously in some higher dimensional mathematical structure. Your childhood will not be gone. Your future would not be unwritten. The people you love who have died would not be truly dead. They would simply be located at different places in the block of space-time, just as New York and Tokyo are located at different places in space, without either city ceasing to exist when you happen not to be there. This is the view of the block universe, or eternalism, as philosophers call it. It has its champions and its critics. Many physicists find it deeply appealing because it seems to be required by special relativity, the relativity of simultaneity, the fact that different observers can disagree about the order of events, is often taken as evidence that all moments of time must be equally real. If your now and my now can differ, then neither of us can claim special status for our particular now. All of the nows must coexist, equally real, equally present, in the unchanging geometric structure of the universe. The philosophical argument for the block universe was made most influentially by Hilary Putnam in 1967 and by Reitdake around the same time. Their argument runs roughly as follows. If two events are simultaneous in some observer's frame of reference, and both of those events are real for that observer, then both must be real in an absolute sense. But special relativity tells us that different observers can classify different pairs of events as simultaneous. By chaining together enough of these simultaneity relations across different observers, you can show that distant future events and distant past events must all be equally real, since they are all simultaneous with some present moment, according to some valid observer. The conclusion, if you accept the premises, is that there can be no objective privileged present, no ontological difference between past, present, and future. All moments must exist equally in a single four-dimensional block. Critics respond that this view cannot explain our vivid experience of time passing, of moments flowing from the future through the present into the past. If all moments are equally real, then why do we experience only one of them at a time, the present one? Why is the present unique in our experience, if it is not uniquely real? These critics, who sometimes go by names like presentists or growing block theorists, argue that time must be more than just a dimension in a static manifold. Time, for them, is fundamentally dynamic. Time really passes. The future is genuinely open. The past is genuinely gone. The presentist view, which holds that only the present moment is real and that the past and future do not exist, has been defended by various philosophers, but faces serious challenges from relativity. If only the present is real, what is the present? Different observers have different presents, so whose present counts? Some presentists try to solve this by postulating a preferred reference frame, a cosmic now that defines what is truly present. But this seems to go against the fundamental principle of relativity, that no reference frame is privileged over any other. The growing block view attempts a middle path, holding that the past and present are both real, but the future is not yet. As time progresses, new moments are added to the block of reality. This view also has defenders, but it faces its own challenges in reconciling with the seemingly observer-relative nature of temporal ordering in relativity. The resolution of this debate is far from settled. It may depend on the ultimate correct theory of quantum gravity, which we do not yet have. It may also depend on advances in our understanding of consciousness, which remains one of the deepest mysteries in all of science and philosophy. The question of whether time fundamentally flows, or merely appears to flow, because of our particular embedding within the universe, might turn out to be closely connected to the question of what it is like to be a conscious observer. These are questions at the very frontier of human knowledge, where physics, philosophy, and cognitive science all converge in a tangle of unsolved puzzles. But whatever the ultimate answer, the journey we have taken reveals something profound about the nature of reality. The simple common-sense picture of time as an absolute flowing background, carrying all events forward at a uniform rate, is almost certainly wrong. This much we can say with confidence. Time is relative. Time depends on the observer. Time can flow at different rates in different locations. Time may emerge from deeper structures rather than being built into the foundations of the universe. And the question of whether space and matter can exist without time, which sounds nonsensical to common sense, turns out to be a serious question that our best theoretical physics takes very seriously indeed. Perhaps the most remarkable insight of all is this. The question of whether space and matter can exist without time does not have a simple yes or no answer. It depends on what we mean by time, what we mean by existence, and what theoretical framework we are using to describe reality. In some sense, space and matter might be able to exist without time. In other senses, they cannot. The investigation forces us to sharpen our concepts, to recognize the subtlety of what we are asking, and to confront the possibility that the universe is genuinely weirder and stranger than we ever imagined. We began this exploration with an image of a frozen universe, all motion ceased, all change suspended. And we have seen that this image, far from being an impossible fantasy, corresponds to something genuinely conceivable within modern physics. A universe without time, according to some of our most sophisticated theoretical frameworks, might not only be possible, but might actually be what the universe really is at the deepest level, with time emerging as an observer-dependent illusion or approximation. The clock on your wall, the years passing in your life, the flow of moments from the future through the present into the past. All of these might be features of how conscious beings experience the universe, rather than features of the universe itself. If Heraclitus was right, and everything flows, then our experience of temporal passage captures something fundamental about reality. But if Parmenides was right, and nothing truly changes, then the flow we experience is nothing more than a shadow, a surface phenomenon obscuring an eternal, unchanging truth. The remarkable thing about modern physics is that it seems to suggest that both of these ancient philosophers captured something important about reality. At our scale, in our experience, everything flows, but at the deepest level of quantum gravity, perhaps nothing truly changes at all. The appearance of change and the underlying stillness might both be real, each appropriate to its own level of description. As you go about your day-to-day, as you experience the ordinary flow of time, consider this. The universe you inhabit may be vastly stranger than it appears. Time may not be what you think it is. The past and the future may be as real as the present. Every moment of your life may exist eternally in some higher dimensional reality. The clocks we rely on, the deadlines we worry about, the mortality we dread, all of these may be artifacts of our limited perspective on a timeless cosmic whole. Or perhaps time is fundamental after all, and the timeless mathematics of quantum gravity is incomplete in ways we have yet to understand. We simply do not know. It is worth pausing to appreciate how deeply these questions bear on our understanding of ourselves and our place in the cosmos. If the block universe is correct and all moments coexist eternally, then in some sense, there is no such thing as genuine loss. The moments of joy and connection that define the best parts of your life are not gone. They continue to exist, just as New York continues to exist when you are in Paris, just as your childhood bedroom continues to exist in the geographic sense, even after you have grown up and moved away. The only difference is that you are not currently located at those particular space-time coordinates. The people you have loved who have died are not erased from reality. They exist eternally at their own points in space-time, living out their lives forever in the eternal block of existence. Some find this view comforting. It suggests that nothing is truly lost, that every beautiful moment is preserved eternally in the structure of reality itself. Others find it deeply unsettling. If all moments are equally real, then the horrible moments are also preserved eternally. Every act of cruelty, every moment of suffering, every tragedy in history continues to exist somewhere in the block of space-time, just as real as anything else. And more than that, a block universe seems to leave no room for genuine free will or moral responsibility, since the future is already laid out as firmly as the past. We do not choose our actions in any meaningful sense if the block universe picture is correct. We simply occupy particular world lines through space-time, following paths that were always there, eternally and unchangingly, in the four-dimensional geometric structure of reality. But in that uncertainty lies a kind of wonder. The fact that we can ask these questions, that we can glimpse even partially into the profound strangeness of the universe, is itself a remarkable feature of our existence. Whatever time turns out to be, whatever the ultimate nature of space and matter, the very fact that conscious beings have emerged who can contemplate these mysteries represents something precious and extraordinary. We are fragments of the universe examining itself, asking what we are made of and when we exist, questions as old as philosophy, and as new as yesterday's research papers. The answer to the question of whether space and matter can exist without time may ultimately be yes, in some deep, fundamental sense. Or it may be no, if time turns out to be irreducibly woven into the fabric of existence, or the question itself may dissolve as we come to understand more about the relationships between these concepts. What is certain is that the investigation is not over. Physicists at CERN and at quantum optics labs around the world, theoretical cosmologists and philosophers of time, researchers working on quantum gravity and on the foundations of quantum mechanics, all of them are pushing the boundaries of human understanding, probing deeper into these questions, gathering new clues about the ultimate nature of reality. And you, watching this video in whatever moment you happen to be watching it, are part of that ongoing investigation too. Simply by asking these questions, by letting yourself be curious about the deepest mysteries of existence, you participate in the long human project of trying to understand the universe that gave us birth. Time may or may not be fundamental, but the impulse to understand, the hunger to know, the willingness to stare into the abyss of these deep questions and wonder, that impulse is itself one of the most remarkable phenomena in a universe full of remarkable phenomena. Perhaps the ultimate lesson of this entire investigation is that the universe is not obligated to match our intuitions. Common sense tells us that time flows, that the past is gone, and the future is yet to come, that space and matter require time in order to exist at all. But common sense developed through evolution to help our ancestors survive on the African savanna. And there is no reason to assume that evolutionary pressures produced brains capable of accurately perceiving the ultimate nature of reality. The universe has repeatedly shown us that its deepest truths are stranger than we can easily imagine. Earth is not the center of the cosmos. Living creatures are made of the same atoms as rocks and rivers. Space can curve, time can dilate, particles can be in multiple places at once. Information can be preserved in quantum entanglements that span vast distances. Given this track record of cosmic weirdness, it should not surprise us that time itself might turn out to be something very different from what it appears. If you enjoyed this exploration of time and the foundations of reality, please hit the like button to help the channel grow, and subscribe for more deep dives into the wonders of physics, cosmology, and the nature of the universe. Leave a comment letting us know what you think about the possibility of a timeless reality, and share any questions you would like us to explore in future videos. Thanks for watching, and we will see you next time.